surprise.
All right. By long tradition, fourth day ends with the fireside chat with the inventor of fourth, Chuck Moore. The fire this year is all fired up and ready for him.
I'm blocking it.
Off we go.
I am pleased to be here, of course. I also have a bit of dust in my eye, so I'm crying. But it will either go away or it will get worse, and we'll see how it works. I've had a lot of fun the last couple months working with the eval board. I didn't get an eval board for a long time because we didn't have any. And as it turns out, I've got number 8. 0008, I think it is. So we're clearly planning on 1,000 or 10,000 eval boards. It's a very nice board. It costs $450, but it's worth every penny because it has all kinds of Berg pin connectors, and you can hook up wires between them, and you can do all kinds of things. You've perhaps seen my board here. It's got lots of wires, a rat's nest of wires on the top of it. There doesn't seem to be any particular interference between the wires, any crosstalk. So I'm getting clean signals, and this is some of them. This is a picture I want to talk about mostly, but I also want to talk about, show you some of the code that I used to generate it. I can put up lots of pictures like this. I can put up the American flag. I can put up a color test pattern. I can put up the Color Forth logo with the 3 rectangles. This is a new kind of video. I showed you video last year or the year before with the Haypress Creek board, and it was jittery. This, you can see, is not jittery. I don't know why. I've done 2 things. First, I changed from the Haypress Creek S40 to the eval board GA144. So it's a different chip. It might be a cleaner chip and not generating so much internal noise. The other thing I did is put up a character clock. Haypress Creek only had a horizontal sync, and each line got increasingly more jittery as you went to the right. Here I've got 50 character pulses in every line, so the video keeps getting resynced and it doesn't have time to generate any jitter. It's a character-oriented display. Now I think the way it is here, there are 18 across, 2 or 3 characters per going across, and 8 down. So there's 3 characters going down. It makes this picture is stretched awkwardly. The nodes are actually rectangular, taller than they're wide, and it shows up on my monitor quite nicely. Blue and gray are used just to isolate the different nodes. They're reminiscent of the Civil War, perhaps. And the white nodes are those that communicate with the outside world. The red nodes are those that are important. And the blue and gray are unused. They're just sitting there. So I'm using, I don't know, maybe about 12 of the 144 nodes. Lots of room for growth. I want to emphasize simplicity in this little talk, as I often do. I think this is extremely simple. I'll leave it up to you to judge whether you agree with me. On the left, there are 2 nodes generating the clock. One is driving a resonator in the fashion I explained a year ago, and generating 10 megahertz. It counts that down to 2.5 megahertz and passes it on to the other node, its neighbor node. And the neighbor node uses that to generate the two things, the character clock and the horizontal and vertical sync. They're all on character boundaries, but that's easy because the spec is generous. I will show you the code for that later. It's a very interesting code. It's a relatively complex thing to do, to generate vertical and horizontal sync. I've shown you video from, I think, every one of the chips I have ever designed. They all seem to converge upon that is a good demonstration of the capability of the chip. And this is yet another one, different in yet another way. The 144 has no memory. Well, it doesn't have no memory. It has a lot of memory. It has 9,000 words of memory scattered amongst all of its 144 computers. But no one computer has more than 64 words of memory. I'm not generating this image from a image stored in memory. I'm generating the image on the fly, line by line, character by character. Every time I need a character, somebody provides it for me upstream. The white node is ultimately responsible for generating, formatting the image. It calls upon its neighbor to the right to help. The white node is 512 in decimal. That would be 514 in octal. And I'm sorry, but that confusion is going to persist for the next N years. Green arrays will say it's 512, and my color forth will say it's 514. So 512 is talking to 513. 513 talks to 514 and 515. If you hadn't realized this, the first number is the row counting from the bottom, and the second number is the column counting from the left. The two right nodes are storing the character set. So they're not involved in putting up this picture. 513 talks to 613. 613 talks to 713. And 713 generates green. That is one of the white nodes, which is going off chip. The white node to the right is blue. The white node to the left is red. So those are the three RGB D to A's that are putting out the colors. They each have 9 bits of resolution, of which I'm using probably about 7, because they put out a signal which goes roughly from 0 volts to 1.3 volts, something like that. And the video spec is 0 to 0.7 volts, so I don't need the range. The red in between the video nodes are wires, what we call wires. All they're doing is passing data from an input port to an output port. So the data has to get from 613, which is just below the white node, left, up, over to get to red and to get to blue. 613 is an interesting node. It does a relative lot of work compared to the other nodes that are basically wires. In particular, it takes a character and a foreground color and a background color from 513. It separates out the colors and sends them to the nodes. Sends all three colors to all 3 nodes. Along the way, the color gets filtered, so in the end, only the red colors go to the red node and only the green colors go to the green node. These characters are formatted into an 18-bit word with a 6-bit character in the low order part, a 6-bit foreground color next, and a 6-bit background color next. Those are sorted out along the way to the path. And that is one of the keys to programming this chip. You have to distribute your data processing, and you may as well do it along the path that is leading to where it wants to go in any case. This is very simple processing. All it does is decide whether it's red, blue, or green and shift things the appropriate way, and do a color lookup table along the way. Each of these nodes is extremely simple. It's doing a trivial thing. Each one is programmed differently, so they aren't making any decisions. They're just doing their thing, shifting right 6 bits and masking off the color. If this was all being done in a single computer, you'd have 1, time constraints, and 2, a lot of code. A lot of the code just dealing with figuring out which thread you were on, which path you were on, what you were supposed to do. So I argue that that is simple. On the other hand, it is using 10 computers or so to do the job, so it's extremely wasteful. But observe, there's 100-odd computers that aren't doing anything. They're just sitting there. So wasteful is not wasteful. It's a question of having resources, using the resources, being generous with them. If I run out of 144 computers here, I got another 144 computers on the other chip that's on the board. There is no problem of resources. What happens is quite interesting, and you can see this most clearly on SoftSim. Characters are pipelined to their destination. They get backed up. The way the communication works is you can write to your neighbor anytime you want, and you'll sit there and wait until he reads it. So you've got automatic synchronization between the nodes that are involved in this data passing. This works better than I had ever dreamed when I designed the first chip that had these characteristics. And a better example, it's a complicated situation. It's really quite simple, but there's no place to start explaining. The leftmost white node at the top is the asynchronous port to the PC. The code which is stored in the RAM of all these nodes that are doing work comes from the PC. It's compiled in the PC and stored in block buffers, and then transmitted across this serial port. The interesting thing about the serial port is that it takes 10 microseconds to send a bit. So the bits arrive very, very slowly. It takes milliseconds to load the chip. All of the nodes in the chip are loaded. All those unused nodes have got my clever message passing code that will accept data and pass it on. It passes it on through a path that is described in the data. That path has got 3 rungs. You can go horizontally and vertically again. Or horizontally and vertically again. You can do whatever you want up to the limits of the format, which are 6 bits per run. So when input comes into the 708 node, the white one, it is passed through that mechanism to all the other nodes that it needs to. Each message has a header, which includes the path, a body of data, which tells it what to store in memory, and some code to execute to initialize its registers. The first thing I do is program all of the nodes on the chip with this message passing code. It is 64 words of code, part of which is dedicated to propagating itself to its neighbor. along the path that has been indicated. So with a small amount of work, which I can show you, but you aren't going to be interested, all the nodes are formatted. Then I start filling in the actual task which the chip is being programmed to do. We have a reset. We reset the chip, initialize all the nodes, and then initialize the application, and then it automatically starts. And that's kind of a magic mystery that it does start, but it does. The last nodes to be programmed are the ones on the extreme left, the clock nodes. Because once the clock starts ticking, everything else better be ready because it's going to take off and start generating a picture. Originally, I had it coming down to here and over to there as the path that was going to program those nodes. Somewhere along the line, I decided that what I wanted to do was program the white node to dump memory. First, I had it dump its own memory. And I made a display, which if I have time, I'll show you, but I probably won't have time. Then I said, okay, now I'll create a path to someone and dump his memory. So I created a path that went over here to node 0. And I wanted to look at the memory of node 0. Well, you can almost guess what happened. The paths necessary to initialize the clock crossed the path necessary to get to node 0, and there was a total blockage. It took me a while to figure out that that was what happened because lots of other things could have gone wrong. But that is a consequence of the fact that the serial port is so slow. I hadn't anticipated that that path would still be active at the time I was actually trying to draw a picture. And yet, of course, it was. Easy to do. I just rearranged the paths so that they didn't cross, and now I can look at the memory of node 0. What happens when you do that, I send a message along the path to node 0. It has code in it. I mean, node 0 doesn't know anything about sending me his RAM. But we can execute code out of ports. So I send two words of instructions, I think it's two, that he executes when he gets them. And those instructions say, set register A to this value, start a 4 micronext loop that is going to return 4 values, starting at A, incrementing each time. 2 words of instructions will do that to a node who is completely unprepared for doing anything like dumping his own memory. Whereupon I get 4 words coming back to 512. 4 words have got to be converted to octal characters and displayed on the screen. That takes a while. It takes a whole horizontal line to do that. So what you end up with is this guy sending out 4 words of his RAM. They get pipelined up to here. The pipeline is pretty full. It probably, those 4 words come up here and stack up in 4 nodes waiting to be processed. And he's long forgotten anything about it when the words are displayed. Now, as I've indicated here, this is a dynamic display. It is truly amazing to me that you don't see any dynamicism to it because it's static. But each character is a 5x7 character. But it's got descenders, so it's really 5x9. But it's got a blank line in between rows, and so it's really 5x10. Except it's really 6x10 because there's a space between characters. So we've got 6x10 characters. The top row, top line of video is going to be the top slice of the characters. Each pixel is so many microseconds wide and 3 lines high. So 3 identical lines are displayed for every character. That requires going back, in the case of the dump, going back to node 0 30 times to get the same 4 characters 30 times so I can display them repetitively, slicing out the appropriate bits for them. This is not exactly high tech. This is the way monitors were built back in the 60s, 50s. Yeah. And it isn't particularly efficient because it's taking all these computers to do it, but it gets done. And once you sweep a little bit of dirt under the rug, it's really quite elegant. That's a dump. First thing I could do is an octal dump of memory. Then I added these 4 red nodes to put up color force source. Given I've got characters, I may as well put up characters. And I'll show you that in a minute. What else did I want to say about this picture?
Is that being generated right now, or is that?
Yes, at 50 hertz. 50 hertz is a funny number, but I figured it was probably pretty good because it would be used in Europe, maybe. And 50 hertz gave me more time to put up more characters. The format of this is 50 characters per line for 25 lines. So there's a goodly number of characters. The next thing I'm going to do, now that I can display color force source, is put more nodes up there close to the serial port and compile color force source. Instead of sending object code compiled on the PC, I will send source code and compile it on the fly and store it in the appropriate node and essentially eliminate the PC. Now, that's something that Greg has in mind for green arrays to do in one way, and I'm doing the same kind of thing in another way. The reason for doing that, I think, is amply illustrated by Leon's description of how you program an FPGA. It's, to my mind, is horribly complicated. The array forth procedures for compiling and passing and simulating, to me, are incredibly complicated. This, I hope, is going to be incredibly simple. It will use my new keyboard, my old new keyboard, with 3 buttons. I mean, this is not required to list color force source. It's not required to compile color force source, but it is required to edit color force source. And so ultimately, I will have the source stored in Flash, and I will edit it with my little keypad, and I will compile it on the fly. And I think that is going to be a simple system in two dimensions. First, it is really going to be much simpler than a PC admits of. Second, it will use enormously less code, 1% the code or something like that. And third, the user interface will be streamlined to the limit. You push a button and a character changes and the whole thing is changed and you've edited something and you recompile it, and I hope that will be simple. I don't expect anyone else to use it. You'll be welcome to, but it'll be a tool from me tuned to my prejudices, and you've got green arrays to support the elaborate and more powerful system. This is going to be stripped to the limit. And let me explain, let me put up some color force source, if you'll excuse me a moment, and I'll explain what lies behind it. I don't have an easy facility for switching applications. And part of that is the fault of the PC array forth. Doesn't make it easy. So memorize that picture in your mind because it's not going to come back. Hooray! This should look just like color force source that you've seen many times. This is the code for the clock driver, which is driving a 10 megahertz resonant resonator, which is a low Q crystal, basically. But you see the red words and the green words and the white words and the yellow words. This has to be simpler than color forth on the PC, because it's an interesting procedure to program these nodes to cooperate with one another and to actually do something useful. You've got 64 words. You've got 256 instructions at max on each of the nodes that are involved in this. You can't have more than, it's not practical to have more than 1,000 instructions or so in order to solve a problem like this. So we've got to simplify it. What I'm using is something that Jeff Fox suggested. It's tokenized forth. He called it AHA. And words that are the instructions of the F18, drop, store B, 4, micronext, semicolon. Those are all represented by a 6-bit token. 5 bits are the actual opcode, and the 6-bit flags it as a token. Words like, well, comments are counted character strings. The red words and the green words that are not instructions are counted character strings. Numbers are a counted string of octal digits. This reduces the complexity of the code in 2 ways. First, it's much more compact. I'm hoping the source code will only be twice as large as the object code would be. And second, it allows the code to be interpreted in a simple fashion. For instance, when I get the word that's represented by store B, I don't have to look it up in any kind of dictionary. It carries with it its opcode, and it carries with it the knowledge that it is an opcode, and I just store it down in the object program. In order to make this display, I had to have a node full of the words represented by each opcode. It's sort of like like a decompile, sort of like the inverse of looking something up in a table. I have to have the table, but the table is there at display time, not at compile time. Just for completeness, let me explain just a little bit about how this drives the clock. We've got a crystal attached to it between a pin and ground. And we bang on the top of the crystal. And we generate a resonant oscillation. Drive is what does that. Drive does a store B and a store B. That generates a pulse. It pulls it high and then pulls it low as fast as it can, which is about 10 microseconds? 5 microseconds, surely. And put that in and then puts a 4 micronext delay before it comes back and does it again. Yes. The word go starts off by driving 11 is really 12 because we count to 0. And 12 is really 6 because we're driving twice inside the loop. It was really, no, 12 is 24. Well, anyway, we hit it a high and we wait a while, and we hit it low and wait a while and hit it high and do that 10 times, and the clock is running. It is amazing it's that easy to start a clock, because I was under the impression it might take 1,000 hits before it started resonating. In order to do that without any parameters, the stack is initialized, so it's got 8 numbers on it, which it cycles through continuously. Those 8 numbers provide the parameters for store B and for 4, and the drop throws away the first one. So it just sits there and cycles. Having done that, it moves into a mode where it pumps, which means it waits for the clock to go high. It triggers on the edge of the clock going high and hits it a little bit to encourage it to stay going high, waits for it to go low and hits it again and make it go low. That's pump, pump. Then ring, ring, it doesn't bother pumping. It waits for it to go high and waits for it to go low, and then and it repeats that indefinitely. So I'm driving the clock quite mildly. I drive it a little bit, and then I let it resonate, and I drive it a little bit and let it resonate. And by changing the balance between how much you drive and how long you let it ring, you can adjust its amplitude. And this is surely a minimum power clock, because it's only exciting it as little as necessary. So that's the code that I can display. That's how the clock runs. And this is quite simple. No? I mean, it doesn't even use all of the available memory. Yeah.
How does that code fit into the right processor? Is there something to address that particular processor when you're opening up all of the pieces of code?
When the code comes from the async line to the PC, it's got a path attached to it, and the path directs it to the right place. You stop just short of your target, and then you prompt your target to accept the code and store it in its memory. Then you prompt the target to, there's more lines of code there that didn't get displayed, because this is one 64 words of source code. And I need to add another 64 words, but I didn't have any convenient place to put it. All right, now this is the video generated by the evaluation board. And bear in mind that each of those characters is being displayed 30 times at 30 hertz or 50 hertz. So you're seeing there's a lot of activity going on, but 2 things happen. One, it doesn't look like it's busy in any sense. And 2, it isn't using any energy to speak of. The duty cycle of these processors, although there's a lot of them involved in the pipeline, is low. The chip does not get warm. I am pleased. I think this is a neat way of doing things. Now, you are going to go away. Thank you very much. And we'll plug this in here and show you some code. These are prettier characters. These are 18 by 24 characters, if you will, instead of 5 by 7. That's the way it goes. This is a block required by ArrayForce that it's block 200 that I'm a little bit upset about. this is how things are compiled. You specify a node, and then you specify the block that contains its code, and it gets stored away for that node. But there's only one of them. And so I have all of these options packed into this one block instead of having a whole sequence of different load blocks with different applications behind them. Here's an example of the way the code is loaded into a node. For the top, there's node 513. It has 41 words of total code. 3E of those words are going to be stored in memory, and the 40 is irrelevant. The path that's going to be transmitted along goes 1 down, 4 right, and you're there, end. And the word code then ships off the code. For every node that I want to have loaded code, I have to describe a line of instructions like that for the for array4th to process. I showed you the code for the clock. There's the complete code. This word init is what loads all the 8 numbers on the stack. And it does that by giving instructions directly to the computer's port without going through the computer's RAM. So up to 017 is the code stored in memory, and the additional code to 025 is going to be executed once at initialization time. Now, the thing that this does when you get down to the word signal under Go, it actually sends a message to its neighbor node 300. The message is meaningless. It's merely a prompt that says, okay, it's time for you to do the next character clock. And this is the code for node 300. Node 300, the key word there is store in the middle of the signal line. The key here is the word fetch, which you see scattered here and there. There's a fetch in sync, there's a fetch in blank, fetch in lines. 2 fetches? I guess maybe that's all. There's a fetch in ticks. Those fetches are waiting for input from the clock node. And the important thing here, and the point I want to make, is that it's simple. It doesn't matter where you are in this code. When you say fetch, you're going to stop and wait for the clock to tick, and then you're going to go on and do whatever you have in mind to do. I was going to combine these 2 nodes into one. There's enough room. These are both only using about half of the available memory. But when I did that, I couldn't figure out any way to provide that communication. The fact that you can reach out from the middle of code to one of your ports and get information that you need to complete that code is incredibly powerful and very hard to simulate without having multiple nodes. So I'm really pleased with that, and I claim that makes it simple. If I had to combine these 2 tasks into one computer, it would get much more complicated. Now we have this word EX, which lets you interrupt a sequence of instructions and run 2 threads at the same time. You're swapping with the return stack. That's what I had planned to use here. But these fetches are inside different words who have disturbed the return stack. They're inside for loops, which have disturbed the return stack. That strategy does not work in anything but the most simple context. But a fetch or a store, going to your neighbors, can be done in a wide variety of ways. There's another thing that I'm not using here, and I will talk about next year, having to do with communicating with your neighbor. Here I am, actually I'm sending a dummy word. If you notice, each fetch is a fetch drop because the value I get is of no interest. You can send data to your neighbor. You can also send instructions to your neighbor, as I indicated when doing, asking node 0 to give me 4 words of his memory. That is a very powerful tool. If I want to go to a particular place in my neighbor node, I just send him a jump instruction. He goes there. He doesn't have to look it up. He doesn't have to test sign bits. He doesn't have to do anything except be prepared to receive an instruction, and then, of course, he will execute it. I plan to use that in the compiler. The compiler has a number of different things it has to be able to do. It has to be able to compile a number, which means storing the number in the next available word. It has to be able to put down a token, which means selecting the slot and putting the 5 bits into it. It has to be able to generate a jump instruction or fix up the address of a jump instruction. And those can all be done quite nicely by telling it exactly what I want it to do. I had planned that the control node would generate the object code. And I found that that is not feasible. There's not enough room to do that in the control node. The control node has a slave node. It merely tells the slave node, put this in the next available slot, and he knows how to do that. So the task has been factored in a useful way, and nobody has to work very hard. And that is the key. None of these guys can work very hard. They don't have enough memory to do anything complicated. We went through torturous exercises expanding the amount of memory. We originally had provision for having 128 words of RAM. And when the guys in Tempe redesigned the computer, they arranged for 256 words of RAM. Those were both mistakes. 64 words of RAM is the right amount. It doesn't let you do anything complicated. With twice as much memory, it would be 4 times as complicated. The code would be 4 times as complicated. And to no advantage, because you're CPU limited. You're not memory limited. You only execute so many instructions. Keep it simple. But the dimensions of simplicity are rather obscure. You look at a wall of C code, and you can't figure out what it does without starting at the top and reading through it. And you do that a few times, and maybe you get it in your head. Unless it's 1,000 megabytes of code, in which case there's no way you can ever get it in your head. With all the goodwill in the world, you can't read through that much listing, let alone remember it. This has got to be the future. Having 144 computers running in parallel is unprecedented. Yeah, I know they've got server racks full of PCs all running in parallel, but not this way. They're all doing a completely different thing than this. This is factoring simple operations into very simple computers and doing it on a macro scale. We can shrink the process. This is 180 nanometers. It's a very conservative process. It's been around for 10 years. We can shrink that by a factor of almost 10 in linear dimensions, which means a factor of 100 in the area. which means we could put, not 100, but say 50 times as many computers as we have in the same size die if we went to a cutting edge process. That's 1,000 computers. There's no reason to do that. We have no demand for 1,000 computers on a chip. We wouldn't know how to program them if we did. First, we have to learn to program 144 computers, and that'll take a couple of years. And by that time, we'll have the funding and the opportunity to, say, use IBM's fabrication to produce a cutting-edge chip. That's fun to look forward to. What would we do with 1,000 computers? I plan to use, well, I told you I plan to make this, put the compiler on chip. So source code comes in and object code gets compiled. The next step would be to put the source code on flash. And then the thing is completely standalone. I don't need a PC at all. I hook up a monitor and my little keypad, and I'm independent. I like being independent because this laptop just died. Why it chose this afternoon to die, I can't imagine. And it's my good old laptop, so I'll probably take it to somebody and say, can you make this work again? You can't get them anymore. Okay. How do we get from here to there? Green Arrays needs two things. It needs the customers and it needs investment. And we've been running on air for 3 years, and that's got to stop. I have a lawsuit pending against Leckrone. We hope you all kicked him. That would be nice to settle. It would be nice if my patents raise some more money that I can invest in Green Arrays. But I'm never going to have the resources to finance Green Arrays, really. So we have to get some outside money.
Or sell chips.
Selling chips is good. I can sort of see the volume of chips growing with time. Hopefully it grows fast enough. But I think basically we need investment capital. Hopefully the app notes we're preparing and the demonstrations we can give, and we can show off the chip to such advantage that we will attract investors. We haven't been able to do that up to now because we haven't had these capabilities. The one thing Greg has mentioned this, I don't know if he emphasized it enough. We test our own chips. We test them brutally. In fact, more brutally than I even think. 'Cause Mark is very good at that, of squeezing out every path and every bit and then verifying that it works. It can do a lot in about a second. We've got a beautiful suite of tests. You go through quickly and verify that memory works in all the computers. And you do this with much the same thing as I have my paths. You have a path, you pass the code along the path, the computer executes the code, and it sends a reply back along the path saying everything is okay by me. And indeed, almost everything works perfectly on every chip we test. Every now and then, I don't think Greg mentioned this, we have had reports from one of the people running the eval board. The eval board runs down to 0.9 volts. You can run it at half voltage and it works, except for writing memory. You can't write RAM at 0.9 volts, but having written RAM, you can crank down your power supply and run slowly, and it works. This is truly amazing. That's more than I thought we could do. So we're working on being able to write RAM at lower voltages, because that's, as soon as you discover the critical obstacle, you can solve it.
The stacks are changing, right? There's rewrite going on in the stack.
I presume. Stacks are easy.
Sure, yeah.
Stacks are changing. They're about the same.
Hmm?
But they're not the same.
Yeah.
RAM is hard. This is the first chip, not first chip, but These chips are the first I've ever tried to put RAM into, so I'm a novice RAM designer.
There was a question, how many transistors per RAM cell?
6. And they're not packed particularly densely. You can do better with commercial RAM, but we haven't had the resources to integrate commercial RAM with our chip. Not sure I would even want to.
How many RAM transistors does it take to equal the current of a pad? For example, the energy that a pad takes in order to drive a crystal compared to what we're consuming in program execution?
Normal transistors are half a milliamp, and that's what we build the RAM out of. The output transistors are 50 milliamps, so 100 times bigger. We have large output drivers. The output drivers also double as protection diodes, so you can't put a voltage on the pin without getting it clipped at the rails. Those protection diodes are very effective. Given we're putting out 40 milliamps from the pad, we can absorb 40 milliamps of current into the protection diodes. It's the same size, the same geometry, it's just running backwards. And we do that. The RS-232 interface that we have on these boards takes 12 volts through a current limiting resistor directly to the pad. And the pad clips it at 1.8 volts, and the rest is lost. Well, in the dropping resistor, there's a side effect to that, and that is that extra current that we're getting has got to go somewhere, and where it goes is into the power bus. And lo and behold, if your power supply can't accept an overvoltage and drop it for you, you're going to be powering your chip through the RS-232. And we can do that to various extents, but it's sad that RS-232 doesn't have enough current on its line, on its handshake lines to actually drive our chip. But the USB does. My board is powered by a USB connector to the PC. So I guess that's what I had to say. Raising money and simplifying the world, making it safe for democracy. As I said, I've had a lot of fun doing this in the last couple of months. At the moment, I am in a quiescent period. My imagination has tapped out. It will come back in another couple months, and I'll get cracking on the compiler, and then on OCAD. I'm thinking I'm going to design a circuit board for the chip, the way I have in mind, using the chip. Just display the circuit board and edit it and make it nice. I think that would be a good application. That was a much easier thing to do than the chip layout. And I am almost out of time, so I better ask for questions.
Got two questions. First of all, before the fetch up there, there's a little vent thing that looks like a butterfly or moth.
That's the Pac-Man.
Cursor.
That's the cursor. Oh, that's oh.
He is set to eat up the word just to his left.
Yeah, there's a little Pac-Man. The other question that goes back to your clock. And the way you're hitting the clock periodically with a bang bang. But I would think that would introduce jitter. And I guess I'm astonished that you were saying that you really don't have it.
Phase lock to it on the readout.
Pardon?
We're phase locked to it by the way it's sensing coming through.
Yeah, but your phase lock should support boards, which
No.
That's right there. That's gate delays away from milling.
Now, what we do is we have a facility for waiting for a pin to change state. And that's going to change state about 0.9 volts. So we hit it, and then we wait until it makes a transition. And within 10 picoseconds or so, we're gonna be synced to that oscillation. Now, the very act of driving it introduces an asymmetry in the waveform. Otherwise, it would be a perfect sinusoid. When we stop pumping it and we let it ring, you've got a beautiful sine wave. And that's what I would do if I really wanted absolute minimum jitter, is I would let it ring as long as I could and then hit it a few times and let it ring some more.
And the waiting for it to come back is actually waiting in a read operation. When the read operation is done, until the signal comes back down again. And it's coming back down within a matter of a couple of 10 picosecond gate moments.
So it's got to be exactly the right temperature. There's no jitter in that.
Well, there's a minor uncertainty in the spectrometers, but it's a lot less than somebody spinning on that company's ever going to see.
Greg is working with a 32 kilohertz crystal, and again, when he gets that working, the duty cycle of that would be minuscule. I'm at 10 megahertz, and so I've got a 10% duty cycle or something like that. Yeah, and I don't care about the wave shape. I only care about the transitions, and it's only video. And if you can't see the jitter in the video, it doesn't. Nothing else matters.
Concerning the printed circuit board that you're intending to lay out, I put in some thought several years ago about maybe using a tile-based approach to make my own circuit boards. Found that the memory requirements for the trace shapes that I wanted to make were just astronomical. Are you going to continue using tiles, or are you planning on an alternative layout?
The problem with tiles is there are so many pinouts. Each device seems to have a different pitch, and they don't fit into tiles any longer. So, very possibly not. I do want to be able to put the chip on the board, and some of these memory chips, which are BGAs, I guess. And I don't see any way to do that in a systematic fashion. But I'm not going to make very complicated boards. My boards are going to be 2 inches square or something, so it's perhaps manageable. Yeah. That's really hard. And even if you come up with a complicated, challenging problem, you don't know there's a market for it. I like to think of voice recognition as a key. I have in mind how to do it, and it's not going to involve any Fourier transforms. But I don't know who would use it for what.
What about Google searches?
I don't have access to the databases to search them. If we're working on an Ethernet interface. Once we get the chip able to talk to Ethernet, then we could have access to an incredible volume of data and maybe do something interesting. $100 or $1,000 probably requires hardware assist. And we can do that, but not without making another chip. Sure.
That's a problem we're looking for a solution. We know that embedded devices need to be able to communicate. We know that every Ethernet switch made will work at 10 megabits on 40 things. And we know that we that driver received the transport. Check. Oh, yeah. And you need really fast switching codes. I mean, our pads are a whole bunch faster than the op-amps, what it's using for antenna units right now. We can slurve in 3 milliseconds, just one. Instead of how the op-amp.
Okay, well, thank you for listening. Let's have a nice dinner.